Welcome back to this series on topology. In today's video, I'll be talking about a basis for a space, which is a collection of open subsets that generates the topology on that space. You can find a playlist containing all the videos in this series by clicking on the info thing that should appear right now. Let's dive straight into the definition. Suppose we have some topological space X, then a collection B of subsets of X is called a basis for that space if the following two conditions hold. First, we want every element of this collection B to be open, and second, we want every open subset of X to be the union of elements in the basis. In other words, a basis is just a collection of open subsets of X such that any other open subset of X can be written as the union of basis elements. In practice, working with a basis for a topology simplifies one's life because one is just looking at a smaller collection of open sets, but because these open sets generate the entire topology on the space, it's often sufficient just to check certain properties for basis elements. On first reading, this might seem a bit abstract, but in fact, if we look at some examples, you've probably been working with bases for topologies already. Our first example concerns metric spaces, and in fact, open balls form a basis for the topology on a metric space. So we recall that an open ball at point x with radius r, which I'll write b sub rx, this is just the set of all points y such that the distance between x and y is strictly less than r. So this is the open ball of radius r centered around x, and now we take the collection of all such open balls for all radii and all points in the space. So this will be our basis, denoted curly b. This is the set of all open balls at x, where r is some positive real number, and x lies in our metric space M. So we'll call the metric space here, we'll call that M. Okay, and now the claim is that this set curly b of open balls forms a basis for the topology on the metric space. Why is this? Well, we need to check the two conditions we had in the definition for a basis. The first condition was that every basis element has to be an open set. And in fact, this is the case because open balls are open in the topology generated by a metric space. Next, the second condition for being a basis was that any open set in the topology can be written as a union of basis elements. And here, this is also the case, rather tautologically, because the open sets in the topology induced by a metric on a metric space are defined as unions of open balls. So if we take any open set, it's already a union of open balls, so in fact, the open balls generate the topology on the space. Therefore, we've shown that this collection curly b consists of open sets and that every open set in the metric space M can be represented as a union of these basis elements, and therefore this collection is a basis. So if you've been working with the topology on some Euclidean space, which is defined in terms of these open balls, then already you've been working with bases for topologies. And in fact, many of the techniques that one uses for working with the topology on Euclidean space transfers more generally to this setting where we have a basis of a more general topological space. All right, our second example concerns the discrete topology. And here we can form a basis for the discrete topology by taking the collection of all singletons. So let's say that we have some space X, which is endowed with a discrete topology. Then in order to get a basis, we make the following definition. We take all singletons, so that's singleton sets containing some element X, where X lies in the space capital X. Again, we have to check the two conditions for being a basis. The first one says that every element of this basis has to be an open set. Now, because we're dealing with a discrete topology where every subset of X is open, in particular, the singletons are also open. So the first condition is fulfilled. Next, we have to check that any arbitrary open set in the space X can be written as the union of basis elements. So let's take some arbitrary open set U of X, and in fact, because we were dealing with a discrete topology, this is just going to be some subset because every subset is open. So now we need to write U as a union of basis elements. But this is easy because U is just equal to the union over all elements Y in U, and then we union over the singletons containing those elements. Now each of these guys in here is an element of our basis, and so we've written U as a union over basis elements. And this shows that the second condition is fulfilled. So in fact, this collection of all singletons is a basis for the discrete topology. I mentioned before that having this notion of a basis will simplify our life in practice, so let's see how this happens. So the first way this happens is using the following proposition, which is called the basis criterion. And it says that if we have a basis B for a space X, then some subset U of X is open if and only if the following condition holds. So the condition is that for each point P in U, there exists some basis element such that the point P is an element of this basis element, and the basis element is entirely contained within U. So this is perhaps a bit convoluted, so I'll draw a picture. So we have some space X, and we have some subset U of that space. And now we want to find out whether this subset U is open or not. And this basis criterion is giving necessary and sufficient conditions for this U to be open. What are those conditions? Well, it's saying that whenever we take a point P in that subset, then there is some basis element that contains P as an element. So this is the basis element B. And moreover, that basis element B is contained within the subset U. So if for every point in U we can find such a basis element that contains P and lies entirely within U, then U is open, and conversely, if U is open, then this condition holds. In fact, this condition might be familiar to you from working with Euclidean space, where one characterization of the open subsets of Euclidean space is that it's those subsets such that if you take any point in the subset, you can still find an open ball containing that point that lies entirely within the subset. So just to clarify, if X, for example, is the Euclidean space R2, and U is some arbitrary subset of X, then U is open precisely when, for each point P, we can find an open ball around P, which is this B, such that that open ball lies completely within U. So this is one way of defining open sets in Euclidean space, and it uses the basis criterion, which is stating that defining open sets in this way is equivalent to just saying that the open balls form a basis for the topology. Okay, so let's give a proof of this proposition. So for the first direction, we suppose that U is an open set in X, and now we let P be some point in U, and we have to show that there is a basis element such that P lies within the basis element, and the basis element is a subset of U. Now we know that because U is open and B is a basis, we can actually write U as a union over some basis elements Bi. Now we know that the point P lies within U, and hence lies within this union over these Bi. So this means that there exists some I such that P lies within Bi. This is just because P lies in U, which is the union over these Bi's, so P must lie in at least one of the Bi's. Okay, so we've found a basis element Bi, such that the point P lies within Bi, and now we just need to show that this Bi is a subset of U. But this follows immediately from the fact that U is the union over these Bi's. So Bi is a subset of the union over these Bi's, which is just equal to U, and therefore we've shown that if we take some arbitrary open set in X and some arbitrary point in that open set, then we can find a basis element such that the point P is contained within that basis element, and the basis element is a subset of U. So far so good. Let's show the other direction. So for this, we need to assume this condition, which I'll call star. So we assume that star holds for some subset U of X. And we want to show that this means that this subset is open. Now, by the condition star, we know that for each point P in U, we can find a basis element such that P is contained in the basis element, and that basis element is a subset of U. So for each P in U, there exists, and now I'm going to call this basis element BP. So this is a basis element with P being an element of BP, and this being a subset of U. What we do now is we consider the following union. We consider the union over all these BPs for every point P in U. Now, on the one hand, the subset U is contained within this union. Why is this? Well, if you take some arbitrary point X in U, well, then X corresponds to some basis element Bx, which contains X. And this occurs in this union because we're unioning over all points contained in U, and so in particular X will also occur in the union. Hence we have this inclusion of U into this union. On the other hand, we also have an inclusion of the union into U. Why is this? Well, it's because of this assumption here that these basis elements BP are contained within U. So if we take some point X in this union, then X is contained in particular in some basis element BP, which is a subset of U, and therefore this implies that X also lies within U. So we've shown that we have both inclusions, so U is a subset of this union, and also the union is a subset of U, and so this together implies that U is actually equal to this union over all these basis elements that are associated to points in U. However, these basis elements, these are all open sets. And we know that arbitrary unions of open sets are also open. So in fact, because we've written U as a union over open sets, this implies that U itself is also open. And this is precisely what we wanted to show. So we started with some arbitrary subset U of X for which this condition star holds, and now we've written this as a union over open sets, which shows that this U itself is open. Okay, so we've shown both directions, and so we're done with the proof. Before moving on, I'd just like to stress how useful this proposition is in practice. It's telling us that if we want to find out whether some subset U of X is open, the only thing we need to check is this condition. So we take some arbitrary point in U, and now we just need to find a basis element that contains that point and is entirely contained within U. And in general, when we work with bases, the sets in the basis will have a relatively simple description. So if we can find such a basis element, this usually just means like actually writing down which basis element you would pick for the point. And this is enough to show that the subset U is open, even if the subset U is very complicated. So we've seen that we can determine whether a subset is open based solely on basis elements. And in fact, the next proposition says that we can actually determine whether a function is continuous, also based solely on basis elements. So the proposition states that if we have two spaces, x and y, and B is a basis for y, then a function, f from x to y, is continuous if and only if the preimage of every basis element is again an open set in X. So remember that the definition of continuity is that the preimage of an arbitrary open set is going to be open in X. However, here we're saying that it's enough for the preimages of the basis elements to be open. Let's see why this is the case by giving a proof. So the first direction is immediate, because suppose that f is continuous. Well, by definition, this means that for any open set in Y, the preimage of that open set is going to be open in X. And well, now we just note that any element B of the basis is open, and hence also its preimage under this continuous function f is going to be open. That's just because that's how continuity is defined. So really the content of this proposition lies in the other direction, and for this I'm going to call this condition that the preimage of these basis elements are open. I'm going to call this star for convenience, and let's suppose that star holds. And what we want to show is that f is continuous, so we need to show that for any open set in Y, its preimage is open in X. So we let U be some open subset of Y. We observe that because B is a basis, we can write U as a union of basis elements. So we are able to write U as some union over basis elements Bi. And now we can consider the preimage. And our goal is to show that this is open. However, because of this equality, the preimage of U is the same as the preimage of the union over these Bi, which, because preimages are compatible with unions, is the same as the union over the preimage of each Bi. Just as a reminder, preimages are compatible with pretty much every set operation, including unions, and if you don't immediately recall why this is the case, you should quickly check it for yourself, but it's a very quick and straightforward proof. In any case, we've now managed to write the preimage of U as a union over these preimages of the Bi's, which by our assumption star are open. So recall again that the union over open sets is itself open. So this entire union is open, and this is equal to this preimage of U, which therefore is open. And so we've shown that for an arbitrary open set U, the preimage of U is open, and this is the definition of continuity, so it follows that f is continuous. And this concludes the proof. So here we again see an example where working with a basis simplifies our life, because in order to check that a function is continuous, we don't need to check that the preimage of an arbitrary open subset is open. We can just restrict ourselves to these basis elements and check if the preimages of basis elements are open. As an example of this, we can think about how we check continuity for functions between Euclidean spaces. So one way to do this is to use the general definition of continuity and take some arbitrary open set in the target and see if its preimage will be open in the source. But this is basically never done in practice because a general open set in the target can be very complicated. Instead, an equivalent characterization of continuity for a Euclidean space is this epsilon delta definition of continuity, which in fact just is obtained by using this proposition together with the fact that open balls form a basis for the topology on Euclidean space. So if you're familiar with the epsilon delta definition of continuity on Euclidean space, you can think about why that definition follows from this proposition together with the fact that open balls form a basis for the topology on Euclidean space. So far, we've been assuming that we already have some topology on X for which our collection B is a basis. So there, the logical order is that we already kind of know what the topology is on X, and now we're trying to find some distinguished collection of subsets such that that collection is a basis. Instead, one could work the opposite way around, so one could start with some set X, which does not yet have a topology on it, and one could designate some collection of subsets to be a basis, and then generate the topology based on this collection. So this is what is done when we define the topology on a metric space. So we a priori just have a set, which is the metric space, together with this distance function. And then we declare the collection of open balls to be a basis for some topology on this metric space. And then we consider, well, subsets that are unions of these open balls, and these are then the open sets in the topology induced by the metric. This might sound pretty straightforward. One starts with a set, one picks out some collection of subsets that one wants to generate the topology, and then one just considers all possible unions of those subsets as the topology on the space. But there's a catch, because not every collection that one might designate to begin with will actually generate a structure of open sets that is a topology. So remember that in the definition of a topology, we have these conditions, namely that, well, the empty set needs to be an open set, the entire space needs to be an open set, arbitrary unions of open sets need to be open sets, and finite intersections of open sets need to again be open sets. And now it's possible that if we choose in the beginning this thing that we want to be a basis for our topology, if we choose this poorly, that these conditions won't hold. So here's where this proposition comes in. And this is giving the criteria we need in order for such a collection that we choose on a set, in order for that to generate a topology on the set. The proposition states that if we have some set X and we have some collection B of subsets of X, then B is a basis for a unique topology on X if and only if the following two conditions hold. The first condition says that X, so the entire space, needs to be the union over all the basis elements in B. And the second condition concerns the intersection of basis elements. It says that if we have two basis elements and there is a point within their intersection, then there has to be a third basis element such that X lies within that third basis element and that third basis element is contained within the intersection. This second condition is perhaps a bit complicated, so I'll illustrate with a picture. So we suppose that we have two basis elements, B1 and B2. So let's say this is B1 and this is B2. And their intersection contains some point X. So in particular, it's non-empty. Okay, so this is the situation we have. Now, in order for condition 2 to be fulfilled, we have to be able to find a third basis element that contains the point X and is contained within the intersection. So this third basis element should look something like this. So it contains the point X and is also contained within the intersection. And in that case, if we can do this for any point X within the intersection, then the second condition is fulfilled. Okay, before proving this proposition, let's just quickly think about how these two conditions are tied to the conditions we need the topology on X to fulfill. So the first condition is tied to the fact that we want the entire space X to be open. And the second condition is related to the fact that we want finite intersections of open sets to again be open. And we'll see exactly how this plays out in the proof. Now, the statement is giving necessary and sufficient conditions for such a collection B to be a basis for some unique topology on X. So one direction is assuming that B is already a basis for some topology on X. And then we'd have to check that condition 1 and condition 2 hold. This is in fact pretty straightforward. So the first condition follows from the fact that we can write every open set as a union of basis elements. So because we know that X is a topological space, X itself is open, and this implies that X is the union over some basis elements Bi, but now because all of the basis elements are contained within X, this is in fact the same thing as the union over all basis elements in this basis. So we know that this equality here holds because B is a basis. So this is known. And this equality is what we want to show. So suppose that we take some element Y in this union. Well, then obviously it's also going to be contained in this union, which is a union over all the basis elements because, well, this is a larger set that we're unioning over. So this inclusion in this direction is clear. On the other hand, if we take a Y in this union over all the basis elements, then because each basis element is a subset of X, Y will also lie within X. So Y will lie within X. So this shows that this big union is a subset of X. But we know that X is equal to this union over the BIs. That's this first equality we have by the basis property. And so we've also shown that this big union over all basis elements, that this is in fact included within the smaller union of basis elements. And this shows this equality that I've highlighted here. So in any case, we've shown this condition 1. Let's move on to the second condition, which says that if we have two basis elements and a point within their intersection, then there has to exist a third basis element such that X lies within this third basis element, and the third basis element is a subset of the intersection. Okay, so we let B1, B2 be basis elements, and X be a point in their intersection. Well, now we know that these guys are open, and hence also their intersection is going to be open. And now we have some point X that lies within an open set. Now all we have to do is think back to our basis criterion that we proved before, which stated that whenever we have a point within an open set, we can find a basis element that contains that point and is contained within the open set. So hence by the basis criterion, there's going to exist some third basis element such that X is an element of the third basis element, and this is going to be a subset of this open set, which is in this case the intersection of B1 and B2. Okay, so this shows the second point and also the direction that if B is a basis for some topology on X, then these two conditions hold. Now let's move on to the other direction, which is a bit more involved to prove. So we suppose that X is just some set, and that this B is just a collection of subsets of X. So in other words, this B is a subset of the power set of X. And now we assume that these conditions 1 and 2 hold. And we need to show that there exists a unique topology on X for which this B is a basis. Okay, so what are we going to do? We're going to define U sub X open if and only if U is a union of elements in B. So this is how we're going to define this topology on X. We're going to say that a subset is open if and only if it's a union of elements of B. And well, this is basically just what it means to be a basis. So once we prove that this assignment actually gives us a topological space, it will immediately follow that this collection B is a basis for that topology. But in advance, we don't know yet that this assignment will actually give us a topology on the set X. So now we need to check all the defining features of a topology. So the first of these is that the empty set and X need to be open. Why would this follow from our definition? Well, the empty set is the empty union over no elements in our collection B. So in fact, the empty set is going to be open according to this definition we've made. So empty set is a yes. And now we need to check that the entire space X is going to be open. But this follows from condition 1, saying that X is the union over all basis elements in our collection, and because, well, it's such a union, it's going to be open by the definition we've made. So also the entire space X is open, that's a check. Now the next thing we need to check is that arbitrary unions of open sets are again open. So for this we suppose that we have some collection of UIs which are open, and now we need to show that the union over these UIs is again open. So that's a question mark for now. Okay, but by our definition, these UIs being open means that each UI is itself a union of basis elements. So in fact, this union over the UIs is actually a double union. It's a union over each UI, and these are themselves unions over some Bij. So we have some double union over basis elements, and this is equal to this union over the UIs. Okay, but this shows that this union over the UIs is again a union over basis elements, so it itself is again open according to our definition. So this question mark is in fact true, and we've shown that the union over arbitrary open sets is again open. Okay, and now the final point we need to check is that if U1 and U2 are open, then their intersection is again open. And this will make use of the second property, and for this I'll also need some more space, so I'm going to erase our hypotheses here, and I hope you'll remember them. Alright, so what we're trying to prove is that if we have two open sets U1 and U2, then their intersection is also going to be open. And now recall that the way we've defined open sets in this thing we want to be a topology, it means that U1 is going to be some union of basis elements, and also U2 is going to be some union of basis elements. And now we're first going to look at the special case where U1 and U2 are themselves basis elements. So we're going to take some B1 and B2, and we're going to show that their intersection is going to be again an open set in this thing we're trying to define as a topology. So for some point X in their intersection, we know that there's going to exist, by condition 2, some bx such that x is contained in bx, and also bx is going to be a subset of the intersection. Okay, and now we're going to apply the same trick we used before in the proof of the basis criterion in order to express this intersection as a union over basis elements. So we're going to observe that this intersection is actually going to be equal to the union over all x in the intersection, and we're union over these basis elements bx that are associated to each point x. And the argument for this is precisely the same as we used for proving the basis criterion. One direction of containment, namely that this intersection is contained in the union, follows from the fact that each point in the intersection is contained in this union by the hypothesis that x is an element of bx, and the other inclusion follows from the fact that each bx is a subset of the intersection. So in conclusion, we've started with two basis elements b1 and b2, and we've written their intersection again as a union over basis elements, which means that this intersection, well, this is a union over these basis elements, so it's open by our definition of what it means to be an open set in this new topology we're defining. So this means that this intersection is actually an open set. All right, so we focused on this special case where we start with two subsets that are already basis elements, and we've shown that then their intersection is again open according to this definition of the topology that we've made. So maybe let's just put that here on the side. So if b1 and b2 are basis elements, this implies that in fact also their intersection is open. And well, what this means is that it's a union over some basis elements. Now moving on from the special case, we considered the general case of arbitrary open sets u1 and u2. And now we write u1 as some union over some basis elements b1i, and u2 as a union over some basis elements b2j. So here the index runs over i and here over j. And now we consider this intersection. So u1 intersection u2, and this is equal to this union over the b1i's intersected with the union over the b2j's. And now by basic set theoretic properties of the union and the intersection, namely that they distribute over one another, this whole thing is equal to the union over the index I and j combined over intersections b1i with b2j. If you want to think about how this expression was transformed, it's easiest to do in two steps. So first you distribute the intersection over one of the unions, and then after you will see that it's an intersection over one of the entire unions with each term, let's say the b2j's, and then one distributes again and pulls out the union over the other index from this intersection and gets this expression. In any case, we can rewrite this intersection over two unions as a union over intersections. Why is this useful? Well, we know from our examination of the special case where we have two basis elements that then their intersection is open with respect to the definition of the topology we're making. So this means that each of these b1i's intersected with the b2j's, this is, well, open in our new topology. So this means that it's a union over some basis elements, and now we need a lot of indices, so it's going to be something like some bk sub ij's, something like that. In any case, each one of these intersections that occurs within this union is itself a union over basis elements, which in turn means that this entire expression here is just a big union over some basis elements, which shows that, well, this intersection U1, U2 is a big union over basis elements, and by our definition of the topology we're defining, this means that this is again going to be open. Okay, that concludes the 3 things we need to check in order for this collection of open subsets we've defined to be a topology. And with that, we're done with this proof. So we've shown that if we have a basis for some topology, then this basis will satisfy the 2 properties 1 and 2. And conversely, if we have some collection of subsets of a set X that satisfy these 2 properties, then we can define a topology on the set X by just saying that a set is open if it's a union of these elements in the collection B. And then the collection of open sets defined in this way will actually be a topology, meaning that they satisfy these 3 properties we need for the topology, namely that the empty set is open, the entire space is open, arbitrary unions of open sets are open, and finite intersections of open sets are again open. And you can see this last part of the proof is maybe a bit convoluted because we have unions over unions of things and so on. But really these 2 properties, the first one is just saying that we can cover the entire space with these basis elements, and the second one is a sufficient criterion in order for the intersection of 2 open sets defined in the way we did to again be open. With that, I'm done with what I wanted to say about bases. I hope that what you've seen today gives you some impression of why working with bases could be useful. And later on in the course, we'll be defining certain topologies in terms of bases because that makes the definitions tractable. And next time, we'll be looking at countability properties for bases.